So hello everybody, and big thanks to the organizers and Andra in particular, because she's been sending us emails at any time, day and night, so she must be exhausted. And so congratulations for everything, and thank you for letting me speak. We've had a beautiful introduction well, not this morning for us, but with the very first talk by Matt Owers, who spoke about jellyfish galaxies. So I'm going to go very quickly on this. He also showed a very dramatic image of MACS J0717, which is a cluster that I'll be talking about mostly. So we've been hunting for jellyfish galaxies in clusters with Simon Chiche, who used to be master's student, who's now a PhD student with someone else, Catarina Lobo from Portugal, and Mathilde Josac from Durham, UK. So I think I'll more or less skip this because we've heard about this during the previous talks. We will skip gravitational effects, that is, we will try to avoid galaxies that are undergoing gravitational effects which affect stars and gas. And we'll be trying to look for galaxies undergoing hydrodynamical effects, which affect only gas, that is mainly ram pressure stripping that we've been hearing a lot about already, where the hot intracluster gas interacts with the gas of infalling galaxies with several effects that are compression along the leading edge of the disk, a boost in star formation followed by quenching, formation of tails of gas in the wake of the galaxy, condensation of star-forming knots, and asymmetric morphologies. So from what I had found, jellyfish galaxies were first named by Becky, but we heard this morning by Matt Owers that there was already a previous name given to these galaxies a few years earlier. But this was based on hydrodynamical simulations. There have been a series of papers by Poggianti and her group based on VLT-MUSE data. So if you're interested in recent results on jellyfish galaxies, you should read those papers. They're extremely nice. And there have been, of course, extended tails that can be seen in ionized gas, but you can also see young stars in broadband filters, and that's what we are going to do. So we've been searching for jellyfish galaxies in a sample of about 40 clusters, up to Redshift almost 1, based on HST data. This is just one example. So our sample is 40 clusters with HST data that have galaxy spectroscopic redshifts, and they come from two surveys, which are the Daftwada survey that I worked on several years ago, and the Clash survey, which is more well known. And in particular, we have MACS J0717, which is at redshift 0.55 with a large HST mosaic with a very high number of spectroscopic redshifts, which is about 600, and with a nice catalog of 8 magnitudes in the optical and infrared. So we selected jellyfish galaxies by looking at all the galaxies with redshifts within more or less plus or minus 2 times the velocity dispersion of the cluster. We selected by eye galaxies that could be jellyfish candidates, and we classified them following the Ebeling classification, that is with J between 1 and 5. This was done by 2 of us, Simon Chiche and myself. Our classifications didn't always completely agree, but usually within a 1, plus or minus 1, let's say. We eliminated galaxies with obvious gravitational interactions with a neighbor, that had a neighbor within 50 kiloparsecs, and where we could see some signs of interaction, tidal arms, and so on. And for MACS J0717, to avoid losing high velocity galaxies, we extended the redshift interval to plus or minus 4 times the velocity dispersion. So we got 81 jellyfish candidates in MACS J0717. You have here the redshift histogram for the entire redshift sample and for the jellyfish candidates in green. So you can see that there's no obvious bias, no obvious difference between the redshifts of the jellyfish candidates and the overall redshift distribution. And this is how they are distributed. So this map is, in fact, a density map of red sequence galaxies that we had drawn in a paper several years ago. This density map is quite consistent with other maps that were drawn based on weak lensing, both by Josac in 2012 and Martinet in 2016. So the red and blue points just correspond to points classified with probabilities, with Ebling numbers of at least 3 by Simon Chiche in blue and by myself in red, or the other way around, I don't remember, it doesn't really matter. You have a scale here, 1 megaparsec, and the black circle is 1 megaparsec radius. So this shows that the full structure is almost 9 or 10 megaparsecs long. So you have the main cluster, which is where the contours, of course, are tighter. And you have a sort of large filament that extends towards the south. And you can see that most jellyfish galaxies are avoiding the cluster center. We have none at the very center and very few within 1 megaparsec radius. This was said before, I can't remember who said it, but it's also found in numerical simulations. There was a recent paper by Yun Pilepich and et al., where they showed also that jellyfish galaxies seemed concentrated more in the outskirts of clusters. So these are just two examples of jellyfish galaxies in MACS J0717. So you can clearly see the direction towards which they're moving, and you can see a clear cut in the direction where they're going. So if we look at the properties for MACS J0717, we can see that they're mainly blue galaxies. On the left, you have a color magnitude diagram. In red, you have the main sequence, which was defined several years ago, and in fact, where the galaxies were extracted to draw the density map that I showed before. And on the right, you have the histogram of the distances to the cluster center. In red, you have all the jellyfish candidates, that is the 81 galaxies. And in blue, you have the jellyfish galaxies with J class of at least 3, that is the most probable jellyfish galaxies. For the other clusters, we found 97 jellyfish candidates in 22 other clusters. That means that out of the 40 clusters, there were a number of clusters where we found no jellyfish candidate. And out of those, we have 31 galaxies that come from the CLASH survey and which have up to 17 measured magnitudes. So why am I keen on magnitudes? Because we analyzed the stellar populations of these jellyfish galaxies. So for this, we made a fit of the spectral energy distribution with with LeFar. So this was done for 79 of the 81 jellyfish candidates in MACS J0717 and for 122 non-jellyfish star-forming galaxies in the same redshift range, in the same data as MACS J0717. So by star-forming, I just mean that they have specific star formation larger than the usual value that separates star-forming from non-star-forming galaxies, which is the log of the specific star formation rate larger than -11. And in the other clusters, we have 31 jellyfish candidates, as I said. So this is typically the models that are fit when we have 8 magnitudes, as for MACS J0717. So you can see that all models except 2 show a faint H alpha. And in more than half of the models, we have all main emission lines included. That shows that there is star formation there. And this is confirmed, of course, by a certain number of quantities. We have stellar population, we have a star formation rate. So here on the left, you have the 79 jellyfish of MACS J0717. You can see that the star formation rate is between 1 and -1, I mean, and 1 point something. Sorry, this has moved without my willing. And you can see on the right, the pink histogram corresponds to non-jellyfish. So you can see that it's much more spread, and you have much smaller star formation rates in a number of galaxies. And for the other galaxies, the histogram in blue shows that the star formation rate is more or less comparable to that in MACS J0717. Then if we look at the specific star formation rate, that is the star formation rate divided by the stellar mass, we can see that almost a large majority of jellyfish galaxies in MACS J0717 are above the limit of -11 I was talking about, whereas the non-jellyfish are spread mainly below -11, or at least a large fraction is below -11, more than half. And in the other clusters, you can also see that the fraction is above -11. So if we look at the age now, you can see that in MACS J0717, the jellyfish are mainly below 1.5 10 to the 9th years. So that is, they're pretty young. Whereas in the non-jellyfish, you have a much broader distribution of ages. And in the other clusters, well, you have a sort of large distribution too. So it's mainly in MACS J0717 that you see that they're young. You also, we also find that the stellar masses are rather smaller in jellyfish galaxies than in non-jellyfish galaxies. They're all included between 9 and 11 in logarithmic scale, whereas for non-jellyfish galaxies, they're more between 10 and 11. And in the other clusters, they're also, the spread is also quite large. So if we look at the stellar, the star formation rate versus stellar mass, we can see that a number of galaxies is above the Peng relation that was derived from the SDSS survey, and also above the Vulcani relation, but they're not all above it. So, and finally, since I see that I only have 30 seconds left, if my chronometer is right, that we are beginning to look at the dynamical properties of jellyfish galaxies. This was mentioned by Yanconi, I forgot his first name, on Monday. And so this is on the left, you have the jellyfish galaxies. On the right, you have a similar plot by Mahajan et al. And we're trying to investigate the dynamical properties. So as a summary, we can say that jellyfish galaxies have rather high star formation rates and specific star formation rates. There's no relation with the J class, that is the probability that they are really jellyfish. The star formation rate is 3 times higher in jellyfish than in non-jellyfish. The masses are between 10 to the 9th and 10 to the 11th solar masses, and they're mostly young. So what we're now doing, and I'll leave you with that, is just to study another cluster with data comparable to MACS J0717. So we hope to get results in a few months. Thank you.